Hello everyone, my name is Yuji Sakamoto. I am an associate professor from Hokkaido University. The title of today's lecture is Introduction to CubeSat Thermal Control System. This is my information. I was working at Tohoku University for 15 years to develop micro and nano satellites. The satellites were developed under the collaboration with Hokkaido University, and they are dedicated to Earth remote sensing. Now, I am working in Hokkaido University, and the collaboration is still continuing. This is contents. Firstly, I'll introduce my activities and provide a background of thermal analysis. Section 2 will cover the theory and the fundamental knowledge to calculate the satellite's temperature in space. I'll add a tutorial session. This is the example of one node thermal analysis for 1 unit CubeSat. Section 3 and 4 are the case studies from my experience in micro and nano satellite developments. They are 50 kilogram microsatellite and 2.6 kilogram 2U CubeSat. These two types of satellites have a different tendency of temperature. This is section 1, Introduction. This satellite is Diwata-1. My team developed with Filipino students and engineers. Diwata-1, this is 50 kilogram microsatellite. This was released to space on April 2016 from the International Space Station. This satellite was a first-time experience for Filipino students. Now, they became the next leaders for young students and professionals in the Philippines. Let me share my experience with you. Firstly, I developed the SPRISAT in 2009. This was a 50 kilogram microsatellite launched by the H2A rocket in Japan. After that, we tried to develop 2U CubeSat, RICO, and the second microsatellite, Rising-2. Then, my team collaborated with the Philippine government and universities. We released Diwata-1 and Diwata-2. Also, we developed the RISAT. This is an international collaboration of scientific mission payloads. This was launched by an Epsilon rocket in Japan. Our microsatellite weight is between 50 to 70 kilograms. This Diwata-2 has 57 kilograms. And the CubeSat is 2 or 3 kilograms. The RICO was 2.7 kilograms. As you know, satellites are classified by weight. ALOS-4, the left figure, this is Japanese remote sensing satellite. This weight is 3 tons. Large satellite weight is more than about 50 pieces of microsatellites, or 1,000 pieces of nanosatellites. I want to emphasize the satellite launch is not a goal of a project. I think it is just a start of operations. We need 1 to 3 years for the development of a new satellite. This is including design, fabrication, assemble, and environmental tests. Then the satellite is handed over to a rocket company. After the launch, the operation will start with the lifetime of a satellite, depending on their missions. My team especially developed the remote sensing satellites, so the satellite needed to observe the Earth's surface and the natural resources. Especially less than 400-kilometer orbit, the altitude of a satellite is gradually decreased. Then, finally, it re-enters the Earth's upper atmosphere. The satellite body will be melted by heat and disappear completely. In the satellite system, there are bus systems and payloads. Payloads are instruments for missions. Missions are sometimes engineering demonstrations, and sometimes for Earth, planets, and deep space observations. There are several missions and payloads in one satellite. It is important to keep the health of the bus system. The bus system is including the structure system, power, communication, computer, and the thermal and attitude system. Before the launch, the structure is evaluated by a vibration test. Post-launch, firstly, the health of power system will be cleared after the stable charge and discharge of the battery. The communication will be verified where we receive the signals from the satellite and check the response to our transmitted commands. After the computer stability is established, we can confirm the typical temperature in the satellite. During the day-night cycles, externally exposed instruments will suffer very severe cold or hot temperatures. Also, temperature of internal instruments and the battery can change up and down. Finally, the satellites will be maneuvered to a target location or direction, and we will consume several days or months to achieve high accuracy attitude control. This is an example of internal instruments. This is a photo of the Water-1 satellite. There are telescope, gyroscope, payload computer, reaction wheels, and this is also star sensors here and here, and the power control unit, telemetry and command computer. This is including an attitude computer, transmitter, and receivers. The dimensions are fixed for satellite released by International Space Station. This is 55, 35, and 55 centimeters. And the mass is finally 52.4 kilograms. If you don't care of the temperature of satellite, please imagine what may happen. If the battery is exposed in very cold situation, discharge current can be zero. The life of battery can be severely impacted. In this case, the missions will end in failure. When the onboard computer and the sensor are exposed to an out-of-range temperature, the stable frequency of the oscillator and the clock devices will suffer from very high or cold temperatures. The disturbance of clocks will stop the proper communications between devices. We cannot receive the telemetry data. We cannot control and monitor the satellite anymore. When the mechanical parts are exposed to an out of range temperature, they can become cracked, broken, or distorted. Sometimes it can change the performance of payload. For example, the telescope or deployable paddles can be broken. If the design phase, it is important to identify which items will have a narrow or severe temperature range. We need to estimate the temperature in the preliminary design phase. It will affect the design of the structure, locations of onboard instruments, and locations of solar cell area. Also, we need to think the space for additional heat control items. In this seminar, I'll talk about the fundamentals of thermal analysis and control. They are from my actual experience of satellite developments. After the methodology section, I'll supply the tutorial section of one-node simple thermal analysis. This will be useful for one-unit CubeSat design. In this seminar, I'll talk about the case studies of analysis, test, and flight data from SprySat, Ryzen 2, and RICO. I hope this seminar will decrease your work time of new satellite projects. This is section 2. I'll explain theories. In this chapter, I'll explain what kinds of theories are necessary to think about the thermal system. Firstly, I list up the elements to decide the temperature of satellites. There is a satellite in space. There is a direct solar sunlight. This heat is input to the satellite by the external panels. And also, the sunlight is reflected by the Earth's surface. This heat is also input to satellite. This reflection rate called albedo. This is solar albedo radiation. The Earth itself, this is a heating object. This radiation heat is input to the satellite. This is called Earth infrared radiation. And the heat of satellite is output to deep space. Around the satellite, there is deep space, which is very cold at 4 kelvins. Through the balance of input and output, the temperature of the satellite is decided. The changing rate of temperature can be expressed by this equation. Here, Q is heat input or output. When sum of Q, the sign is plus, the temperature T can be increased. The sign is minus, this can be decreased. When Q becomes 0, the temperature is not changed. The temperature can be converged to the temperature, specific temperature. Please think if there are two objects and they are connected, by something. Their heat can be transferred between them. At the first time, if T1 is larger than T2, by exchanging their heat, finally, both objects will be the same temperature. Now I'll talk about heat transfer inside of satellites. There are many instruments and structure parts of a satellite. We define each item by symbol I. We needed to think for each item I, sum of consumed power or heated power, this QI, and contact heat transfer and radiation heat transfer to other items. For inside items, there is no direct solar light, no albedo, and no Earth infrared light emission. Inside items, they are connected to other inside items or inside all panels. When an instrument consumes an electric power, the same power can heat the instrument. When you put an additional heater material, it can be included in this cube. In following slides, I'll continue to explain the contact heat transfer and radiation heat transfer. The two important elements I explained that decide the volume of heat input and output. The symbols are alpha and epsilon. Alpha is the solar absorptivity, and epsilon is infrared emissivity. They are defined by 0 to 1 no unit value. Left figure explains the meaning of alpha value. When the solar radiation hit QS, the value is 1,366 watt per square meters, and alpha is 0.9. In this case, absorbed heat in panel is 0.9 QS, and other 0.1 QS is reflected to space. When alpha is large, the heat input from sunlight can be large. Right figure explains the meaning of epsilon value, especially for the radiation heat QSP to space. QSP is proportional to epsilon value. Comparing two panels, the one is 0.9 and this one is 0.1. In this case, the radiation heat, output heat of upper panel is 9 times as bottom one. Earth infrared heat is input to panel, and it is also proportional to epsilon value. But this output heat has more impact. This is larger than input heat. I'll talk about the contact heat transfer. In the satellite, a lot of items are directly connected. Please imagine two mechanical parts fastened by a bolt. This is bolt. You can imagine these two objects will exchange their heats through this contact surface. We can model the speed of heat transfer by contact using thermal resistance, this one. The unit is watt per Kelvin. When temperature 1 is larger than temperature 2 at the beginning, the heat is transferred from 1 to 2 at first. This heat, Q12, is expressed by this equation. This is proportional to thermal resistance and difference of T1 and T2. After the passage of time, the temperature T1 and T2 become same. And Q12 can be 0 in final. The next is about radiation heat transfer. Even if two objects are separated, radiation heat transfer exists between them. The transferred heat is proportional to epsilon of each panel, and the view factor 1,2 and area of panel 1. This is Stefan Boltzmann constant value, and the difference of fourth power of each temperature. Now I'll explain the view factor. Please imagine an opposite person's face. When he is nearer to you, you can feel his heat. This means the view factor is high. This is depending on the distance or tilt angle and area of opposite object. When he is far, you cannot feel his heat. The view factor is small in this case. I think you have seen the black painted surface of a component. A black surface has a high epsilon value. You can understand from this equation, heat transfer in same time can be larger by high epsilon value. We can control the amplitude of temperature temperature trend by insulation technique. On the left of this figure, two panels are connected by a bolt. When each object is an aluminum plate, heat will be rapidly transferred. Then the amplitude of their temperature can be similar, like this. By inserting a glass epoxy plate between two panels, and also a glass epoxy washer is used. In this case, direct heat transfer between bolt and plate can be decreased, can be small. Then the amplitude of the internal temperature can be suppressed, like this graph. I think this is a very important technique to control the temperature of satellite components. For example, please imagine this T1 panel is exposed to space and the T2 panel is inside, and a lot of instruments are attached. Temperature T1 will have large amplitude, but the T2 amplitude can be suppressed, and the instruments can be kept in mild temperature situation. I will now switch the topic to the orbital motion of a satellite. In the case of low Earth orbit, the satellite completing an orbit within 90 to 100 minutes per round. The satellite is flying around the Earth of a total of 14 or 15 rounds per day. In a single round, there is roughly a 60-minute sunshine phase and a 30-minute eclipse phase. So this is 60, this is 30 minutes. The exact timing is depending on the attitude and inclination of the satellite. In the sunshine phase, satellites will absorb a lot of heat from the sun with added reflected heat by Earth's surface. In the eclipse phase, the Earth is still emitting infrared heat. This is existing also in sunshine phase. Basically, a lot of heat is emitted from the satellite to deep space in eclipse. So this input is small. So the temperature is increased in sunshine, but decreased in the eclipse. So white figure shows the very special case for only International Space Station satellites. The orbit has a 51.6 degree inclination to the equator plane. Around the summer and winter, the insertion to the equator plane, this is the insertion from sun. So from the sun, the orbit can be seen in all the time. During this timing, the satellite will not enter an eclipse phase for several days. This is only sunshine phase. Heat balance of this phase is completely different from a typical phase. So this is typical phase. There is sunshine and eclipse, and the temperature can be up and down. But in all sunshine phase, it will converge to highest value. This phenomenon cannot be ignored for ISS satellites. It is a very important requirement. In satellite bus system, there is a power system. This power generation and consumption is strongly related to thermal analysis. Please see the left figure, which has a solar panel in the center. Input QS from the sun is calculated from the alpha of solar cells. When power cells with an efficiency of 30%, it means maximum 0.3 QS can be converted to electrical power. This power does not remain in the panel. So in thermal analysis, we need to think the input heat is 0.7 QS on the solar cells part. Then another 0.3 is used in the internal components or is used as charging power for battery. In this case, solar cells are working at the maximum power generating point, 30%. When the battery is fully charged and the bus consumption is only 0.1 QS, power generation at cells can be decreased to 10%. This value is just maximum value. So this can generate the power also in 10% or other less than 30%. In this case, the 0.9 QS to hit the panel. I also talk the case of eclipse. There is no solar light to solar cells. By discharging the battery, the power is supplied to other components and they are consumed. This consumed power will heat the inside of the satellite. So this is the summary. Input heats QS to panel. The battery consumed by bus instruments in sunshine phase, and the battery used to charge battery in sunshine phase. But this is not heating anything. Just charged to battery, and it is discharged in eclipse phase. And this consumed power can heat something, the panel's instruments. This is the final slide of section 2. The Earth is rotating around the Sun, and the distance to the Sun is changing in seasons. For example, in spring and autumn. This one, vernal equinox, autumn equinox. The power flux of the Sun is 1,366 watt per square meters. But in summer, this distance can be far, and this value can be decreased. And the winter is, this can be highest value. Also, Earth's infrared heat, QI, and the rate of solar albedo, A, can have this kind of range of values, the max, minimum, and average. So in thermal analysis, we needed to calculate the estimated temperature range for the highest and the lowest combinations, and the lowest combinations of these values. And we needed to confirm they are existing in the required temperature range of each component. This is tutorial session. I'll explain a simple analysis tutorial in the case of 1 unit CubeSat. I expect you to try the same calculation by yourself. The left figure represents a 10 centimeter 1 unit CubeSat. The surface area is a total of 0.06 meters square. Quickly analyzing the temperature of this shape is very difficult because we need to think about the altitude, as the cross-section area is depending on the altitude. By ignoring the altitude and unstable cross-section area, the shape is replaced by a spherical shape as in the right figure. The surface area is the same as the left figure cubic. This means the radiation heat transferred to deep space is the same as the left figure. And also, the cross-section area with the sphere diameter is used for the input heat from the Sun and the Earth. This one. This tutorial covers two different cases. Both cases have two solar cells. The total dimension is 8 by 7 centimeters of the solar cells. Case A, outer gray region, this region, represents an aluminum surface material with an iodine coating. Case B, The solar cells are common, but the outer this yellow area represents a cover of polyimide film. Firstly, we list up the alpha and epsilon of each material. The material is solar cell, aluminum, and polyimide. Then the occupancy rate in this rectangle area is calculated, this one. So the total area is 10 by 10 centimeters. And this solar cell area is 56% area. From these values, the average alpha and epsilon in the surface can be calculated. So these are average of each materials. Case A has 0.62 alpha and 0.45 epsilon. And the case B has 0.74 and 0.78. The input heat in case B is larger than in case A because the alpha is larger. But the output radiation heat is also higher. Please estimate which case can be higher temperature and how degrees Celsius it is. To this satellite, 3 major input heat sources exist. First is solar light, this one, QS. Second is Earth infrared emission, QI. And the third is albedo light, QA. Each one is derived in an equation, like this one. Here we can replace A cosine, this one, A cosine theta. This is replaced by the A cross in the sphere model. Other constant values are GS, direct solar flux, and the QI, Earth infrared emission, A, albedo rate, and FE, view factor of Earth, and KA. So FE and KA are depending on altitude, and the detailed equation is skipped here. Please refer to a general handbook for spacecraft thermal analysis. By using these equations and also the average alpha and epsilon, the input heat of QS, QI, and QA can be calculated like this. So each one is different in each cases. The total of these 3 is input heat in the sunshine phase, and only QI exists in the eclipse phase. This is step 3. We calculate the D temperature by D time as an example. In this tutorial, power generation by solar cells and the power consumption by onboard instruments, they are both emitted. That is, there is no power generation on this satellite. This is an equation to show the change rate of the temperature by every second, this one. The left term, M, this is the mass of the satellite, and the CP, this one, specific heat of aluminum. The right term is input heat QS, QI, QA, and the power consumption QE, and QSP. This is the radiation heat to deep space. This QSP is calculated by the equation, by this equation. So if epsilon is average emission rate, and A is the total surface area, and the sigma is this one, Stefan Boltzmann constant. So T, this T is the satellite temperature, and the TSP is the temperature of deep space. It is just 4 Kelvin. By assuming the satellite temperature is 20 degrees at first, and other values are assumed in this table, then Q and QSP and dt by dt are calculated like this. So each Q in sunshine or eclipse phase does not change in each phase. But QSP, this one, and the dt by dt are changing every time. Of course, the satellite temperature T is changing every time. As you can see in the sunshine phase, dt by dt has a positive value. This one is positive. And in the eclipse phase, this is a negative. So in the sunshine, T is being increased, and in eclipse, it is being decreased. This is a result of the total of 90 minutes. So this is the satellite single orbital period. The first 60 minutes in the sunshine phase, and the latter 30 minutes is the eclipse phase. The time step is 10 seconds. So 0, 10, 20. So the next temperature T, this is the T, is added 10 times of dt by dt to the previous value. So dt by dt is calculated, so 10 times of this value is added for the next T. This can be calculated by a general spreadsheet, so you don't need to have any special analysis tool for this quick thermal analysis. This is an imitation of one orbital cycle, so the first temperature and the last temperature should be the same in a stable condition. So I said that yes, initial value was 20 at first, but the last value cannot be 20. So in this case, yes, I started from 15.94, then the last one is also the same value. So this means that I found the stable trend of the temperature. We changed this initial T and checked the last T and manually adjusted. So finally, it will be the same value of the initial value. This history of temperature in each case is plotted on the graph. Case A, which one? This one. Case A is changing in the range of from this is about 15.9 to 32.4. So case A is there is the bare aluminum surface. So case B is covered by polyimide tape, except for the solar cells. So case B is very low. The range is from -21 to -4. So as you can see that there is total 36-degree difference between them. So without the insulation concept, so the both cases, I didn't mention about the insulation of inside. So everything is connected directly in this approximate model. So in this case, possibly the inside materials can also change from 15 to 32 degrees. So this result shows the importance of the choice in surface material and applying an insulation concept. So by adding the insulation plates or washers, so inside instruments can be stable like this. Okay, this was the tutorial session, but please try to calculate by yourself. So next one is the case study of 50 kilogram microsatellites. So the orbit is the sun synchronous. Yes, firstly, I'll introduce two microsatellites, the SPRISAT and Ryzen 2, developed by Tohoku University and Hokkaido University. SPRISAT was personally my first launch satellite, and Ryzen 2 was launched 5 years later. So both satellites were developed for remote sensing, and the orbit is sun-synchronous. The satellite altitude were different, 660 and 620. The weight of both satellites is similar. Sprite was 45 and the Ryzen 2 was 43. So as you can see in these photos, there is a space with 3 centimeters in top surface in this area. And also we needed to prepare the 5 centimeter clearance on the bottom. So there is a rocket interface in central part. But finally, this side dimension is 42 centimeters. And other side is 50 centimeters. So both satellites were launched by the same model rockets, so this regulation was the same. This is the inside image. A common concept is having 6 external panels and plus a central pillar. This part, central part. So most of the instruments are attached to the central pillar, and the pillar is thermally insulated by inserting the glass epoxy plates, and as I explained, that there are the glass epoxy washers. So this connecting part are thermally insulated. The point of difference, however, is SPRISAT uses aluminum skin and the core honeycomb panels. So these panels are different. So this design has the greater stiffness. The SPRISAT has the honeycomb panel has the greater stiffness and very lightweight. So there is a lot of merits, but it was not applied to second satellite because it requires a long fabrication period, and we need to negotiate with special company, and the price can be increased. So I changed the process of the panels. So these panels are just aluminum grid panels. So we can have the choice of a lot of manufacturers, and the total cost can be kept in reasonable level. So the next one. This is an inside photograph of each satellite. In the case of SPRISAT, all surface of the components and the panels, they are painted by black. And the Ryzen 2 is different. We didn't paint the inside. So in the left case, actually, we didn't understand the reason why the inside of general satellite is black. Of course, we need to connect the radiation heat transfer. Yes. But this treatment has an opposite effect for the insulation concept. So because this connecting part is insulated, but this surface is connected by radiation heat transfer. So it is very strange concept. So changed the perfectly, the central part was insulated in second satellite. Not perfect, so the moderately insulated. Even if when we use the insulation materials, the contact heat transfer cannot be zero. There is a smaller value. So to achieve the insulation concept, we didn't use the black paint in second satellite. Next one. These are photos of space-sat external panels. This is the top and the side. There are 4 panels of this photo, and this is the bottom. So as you can see, the top one has a smaller area of solar cells. So there is other spaces. And some external components are installed. The side panels there are 4 panels of similar appearance. As you can see, there is a solar cell area and a bit polyimide area and the aluminum bare area. So this polyimide tape is important to cut the electric connection between solar cells and the surface of the panel. So bottom part, yes, the most of area is covered by MLI, multi-layer insulation. So this has the very small value of alpha and epsilon. So there are scientific payloads. So we wanted to keep the temperature without any, we avoided the amplitude of the up and down of the temperature in this part. So I list up the values of alpha and epsilon for each material. Solar cells, yes, this value is already subtracted 0.17. This is the power conversion rate efficiency. So the other 0.68 is counted as the thermally heat input for the panel. And aluminum is 0.26 and 0.03 epsilon. So this is very small. MLI is both values are small, and the polyimide is both values mid values. And we can calculate the average alpha and epsilon for each panel. These values. So these values are used for the simple thermal analysis. So these photos show the same satellite during the development phase. Both satellites are rising too. The left one, as you can see, the surface area is fully covered by polyimide sheet. But the right one is they are removed. So I think using polyimide tape on the aluminum surface, it is very important to, as I said, to cut the electrical connection. And normally the manufacturer pastes the tape at first and cut off excess tape after or before the installation of solar cells. The right photo shows the appearance after the cut of unnecessary tape. The difference between these images may appear small, but in heat analysis, the difference of average temperature is 9.6 degrees. I think performing an adjustment of the polyimide tape area is a very easy method to control heat balance. As an example of this is that the average temperature can be decreased. Can be increased by cutting the polyimide tape area. Polyimide tape has a high alpha value, and but the epsilon is also high. So finally, this can radiate more heat from the satellite to space, as I explained in previous tutorial session. So it is difficult to add an active method to control heat transfer in micro and nano satellites. So the surface tape areas are very important control method. Here, let's look at the very simple thermal analysis method. So I guess the simplest one was the tutorial session. I explained that there is only one node satellite. So this example is two nodes satellites. So one is the surface panels, and the second is the inside structure. So these are thermally insulated in this satellite. So environment of the sun and earth and space. So this is not counted as a node. So the nodes are, first one is this one and second one is this one. In this method, the two nodes are the satellite surface panel and the inside structure. Each has an individual time-varying temperature, and we can calculate the temperature time history in the sunshine and the eclipse phase. For the first node, the satellite surface has radiation heat transfer with the environment. So yes, there is radiation heat transfer. We can calculate the surface area and average alpha and epsilon values. For the second node, the inside structure has contact heat transfer. Sorry. Under the installation concept of the central pillar, we can ignore the radiation between external and inside structure. So we can divide the total mass into node 1 and node 2. For example, in case of the riding 2, I think the one is 15 kilograms and the second is 5 kilograms about. So this figure shows the same relations between the environment and the node 1 and the node 2. We define R, the coefficient of radiation heat transfer, and C, contact heat transfer coefficient. So some instruments will consume power, and they are defined by Q1 and Q2. So the area A and alpha and epsilon for the external panels only. So for internal panels and instruments, we don't need to care for these values, because there is no radiation heat transfer between node 1 and node 2. Here you can see the comparison of the estimated and actual flight data temperature results in the case of SPRISAT. This is SPRISAT. The left figure shows the estimated temperature in 3 orbital revolutions. So this is 1, 2, 3, 3 rounds. So this temperature is, yes, there is no up and down. So because this is the temperature of central pillar, so it is insulated with external panels, and the central pillar temperature is a very mild trend. So top one is the winter season, the bottom one is the summer season. So there is differences about 10 degrees Celsius. So this average value in winter is 16.5 degrees Celsius. So this is comparison of the SPRISAT flight data. So there was, yes, this horizon axis is different. This is the time from sunshine beginning. So this is the 0 minute, and this is the 90 minute. So, or possibly this is the sunshine area, and this is the eclipse area. So in actual flight data, the central temperature was mild trend. So there is no strong up and down. And this average value was 16.5 sorry, this is the estimation, and this is the actual value, average at each time. So I can say, yes, the operation value is a bit higher than estimation, but mostly they are the similar trend. So from 15 to 20 degrees Celsius. So this is a comparison of SPRICE-SAT estimation and the RIDING-2 estimation. As I said, yes, the RIDING-2, the insulation concept was strictly it is increased. So the estimation temperature is also increased in RIDING-2. So the RIDING-2 winter season, the central pillar is 24.3 degrees Celsius. So about +8 degrees Celsius was estimated. So yes, I repeat this one. They have the similar external dimensions, but RIDING-2 average temperature was higher than SPRICE-SAT. The one reason is the power generation efficiency of solar cell. It was higher. So the RIDING-2 was about 28%, and the SPRICE-SAT was only 18%. So the inside central pillar is had the larger consumption power in RIDING-2. Also, yes, the heat radiation among the inside parts were insulated without black paint. So I talked the purpose of completing a thermal vacuum chamber test. The left one is a SPRICE-SAT, and the right one is a RIDING-2. The setup and the measurement time varies between several days to 1 week. So during this test, we need to watch the state of the chamber and the satellite for 24 hours. So this is very draining work for developers. Anyway, this facility is used for two purposes. One is simply for thermal testing of onboard instruments and the harnesses. This is carried out for either the engineering model, this is engineering model, or the flight model, this one, or both. Yes, the operation of the instruments must work normally in both the lowest and highest temperature. The lowest temperature commonly range between the -10 degrees or -30 degrees in some missions, so sometimes lower in the very extreme cold. During the test, we can encounter some troubles such as unstable oscillator clocks. Yes, I will here. And halting data flow. The testing for deployable mechanism is mandatory to ensure safety for these operations within the temperature range. The second purpose of this facility is used to determine the coefficient of heat transfer. This does not require a flight model. I think the dummy Mars is kind of this evaluation model, and the inside instruments can be replaced by the aluminum block, so it can be applied. The number of unknown variables should be decreased, as I think it's better to limit the contact heat transfer coefficient. The left figure shows a test for the SPRICE-SAT flight model, I said. So we need to prepare this heat cage. We call this one heat cage, because it was difficult to paste the heaters on the surface of this flight model panel. But in the engineering model, yes, we pasted this. This is the ceramic heaters. So we can easily input the heat from outside the power instrument. So in the SPRICE-SAT case, we tried to determine both the radiation and the contact coefficients, but the precision of each variable was poor quality because there were many unknown variables. So the right figure, we decreased the number of the estimated variables. So there was only the contact heat transfers. The solar absorption alpha, and the emissivity epsilon. So this can be measured by this kind of instruments. So this is the product of company. So by using these ones and the vacuum chamber test, so estimation precision of the temperature in space can be improved. Okay, this is the final section, the case study of the 2.6 kilogram CubeSat. The Tokyo University developed the 2U CubeSat vehicle. The satellite has two deployable payloads, this one, with technical demonstration payloads. So the satellite was released from the International Space Station at an altitude around 400 kilometers. In this satellite, we honestly didn't have sufficient thermal analysis technique. So there was no special treatment to adjust the temperature before the flight. No insulation concept was applied. So all the structures and instruments are simply connected by stainless ball directly. Yes, the left one is the simulation result, and the right one is a flight data. So this satellite has an all sunshine phase, this one. So this is a different point from the sun-synchronous orbit. So we estimated that it will be plus 43 degrees Celsius. In the typical sunshine and eclipse phase, the temperature range in winter, it will be plus 4 to plus 15. And the summer season is from minus 10 to plus 3 degrees. So negative temperature can have a problem for battery lifetime and the functioning of charge and discharge. We could estimate a very cold situation in this analysis, but we couldn't find any good solutions to increase the temperature because not enough space to control the epsilon of surface and a very poor power generation to use heaters for battery. The right graph was actual data, flight data. So this horizon axis is the 4 a.m., 12 p.m., 8 p.m., 4 a.m. So of local time. And this is the sunshine, and this is the eclipse phase. So yes, by ignoring this plot, yes, this trend is like this. So this blue rectangle is the estimated range in winter, and this is the flight data of winter. This is the bottom. Yes, that is the top. Actually, the flight data show the more lower average temperature in winter season. It means that yes, in summer, yes, that this satellite is exposed in very cold situation. So this is a lesson learned. So actually, this satellite survived in the winter after deployment, winter, spring, and around the summer season. We found the battery was very cold, and yes, it stopped to send the telemetry data very often. So we couldn't get enough data in summertime. So the main reason will be this battery failure in very cold temperature. So this is lesson learned. I think that yes, anyway, one treatment is to add insulation concept. Then the temperature of battery can be stable in more more than average of this distribution. But the temperature in summer can be negative degree, even there is the insulation concept. So we need to prepare a heater for battery, even if the power resource is very limited. Okay, yes, this is the conclusion of this seminar. I'll repeat the most important sections in this lecture, so please take note. Firstly, in section 1.3, I explained the importance of estimating the satellite temperature and adjusting it. If a battery temperature is out of the normal range, the charge and discharge functions can malfunction, and the lifetime of the battery will be shortened. Also, computer sensors and mechanical parts will have problems in very hot or cold temperatures, which can result in mission failure. The result of thermal analysis will have an effect on the design of the structure, the location of onboard instruments, and the necessity of heaters. In the early phase of design, we need to start the thermal analysis, and we need to suggest improvement ideas. In section 2, I explained some theories to be needed in thermal analysis. Satellite temperature are decided by the balance of heat from the sun, the earth, and radiation to deep space. Also, the consumption power of internal instruments and the concept of insulation for them can affect the temperature. That is, thermal analysis is related to power management and operation plans. I would like to also emphasize the importance of section 2.3, insulation method, 2.4, radiation control by surface material, and 2.7, power generation. In section 3, I introduced the case studies of 50 kilogram microsatellites. The first satellite had an ambiguous concept in thermal control, which was improved in second satellite. In our satellites, most instruments are located in the insulated central pillar. But this is one of many thermal concepts. So please refer to other satellite cases and please choose the best one to fit with your satellite. In section 4, this was the case of a CubeSat. Honestly, the battery temperature was often lower than 0, and we noticed the battery wasn't discharged normally in a very cold situation. This case was not a successful example, but it is a good learning opportunity. If we added the insulation materials, at least the operation could have been more stable. The reason we didn't add insulation materials, it was due to the risk of the high temperatures associated with the old sunshine phase. So we must be careful of the balances. I'll finish this lecture. Now, please note that I intentionally included a lot of special knowledge not written in general guidebooks. I am happy you obtained a lot of hints for your satellite development. Thank you very much.